Alright, let's talk about 2.3. This is an introduction to techniques of differentiation. Um, and pretty much the rest of the chapter is going to be about different differentiation techniques. But this is where it really starts to get fun, in my opinion. This is where calculus really starts to get fun. So, here we go. First of all, I'm going to be using this notation in the statements of each of these theorems. That's just because this is the way that your book notates it, and I don't want to confuse you by giving you a different notation than what they're using. But just recall that this means the same thing as f prime of x, right? So this is just the derivative of f of x, okay? So, first of all, the derivative of some constant number, right? Notice that this number in here, it's not dependent on x at all. So if you just have some constant number and you take the derivative of it, you're going to get 0, right? And that should make sense if you think about it graphically, right? If you think about like a graph of a constant function, maybe that's c. Well, it has slope 0, right? The slope of that function is rise over run, so it rises 0, right? And so its slope is 0. So yeah, so that function is going to have a derivative of 0. But to prove it, you can prove it using the limit definition, right? It's a pretty simple proof. Okay, so for example, let's say that f of x equals 4, right? Not f of x equals 4x or something like that, but just straight up f of x equals 4. Then in that case, f prime of x is 0, right? So that's the first little building block. Here's another important building block as it relates to these constant values. If you have some function that you're multiplying by some number, like say you're multiplying the entire function by like 3 or something like that, well you can factor that constant out before you take the derivative. Okay, and again, here's a proof of that fact, right? So if you think about limit, or if you think about the derivative of c times f of x, it would be limit as h approaches 0 of c times f of x plus h minus c times f of x divided by h. Well, of course you can factor out the c, right? You can factor out the c from the numerator, and then properties of limits, right? You can take that c out of the limit and just put it out in front, right? And then this thing, of course, is just the derivative of f. Okay, and then one more building block and we'll practice a little bit. This one's called the power rule. The power rule says if you're taking the derivative of some function or of some monomial, right? This is a monomial. So if you're taking the derivative of some monomial, you can pull the exponent down and then subtract 1 from the exponent, and that's the derivative. That's the derivative. The book gives two versions of this rule. It gives a version that's 2.3.2 and then 2.3.3. The only difference is that in 2.3.2 they are limiting the exponents to be positive whole numbers. But in 2.3.3 they point out that actually that rule works for any real number, and so I'm just giving the more general version of the rule, right? Because it'll work for any real number. I'm not going to prove this one. It's a little more complicated. You can look in the book for the proof of the case when you have a positive integer, but in the case where you have like a full-blown just like real number, like square root of 7 or something as the exponent, that's a little bit more complicated to prove. So I'm not gonna take you through all the gory details of that. But I do want to practice a little bit. Let's practice calculating some derivatives, this time using the shortcuts, so we don't have to use that limit definition in this section. Here we go. So let's calculate the derivative of f of x equals x squared. Right? So this is a monomial, and as we saw in the power rule, if you're taking the derivative of a monomial, you can just take the exponent and move it down in front, and then subtract 1 from the exponent, right? So you just get 2x to the first power, or in other words, 2x, right? So that's the derivative of f of x equals x squared. By the way, you could go through the limit definition and prove that this is true, right? So you could do, limit as h approaches 0 of f of x plus h minus f of x over h, and make sure that you get 2x, but you should be able to get 2x still. I'd probably ask you to do that on a test or a quiz or something, like make you do it both ways. Those are the kinds of questions that I like to ask. Anyway, so if f of x equals x to the fifth now, same trick, right? F prime of x is going to be 5x to the fourth. Okay, let's say that you've got f of x equals 2x. Okay, so this time we're going to have to use two different rules. We're going to have to use the constant rule, and we're going to have to use the power rule. So really I'm thinking of this as 2x to the first power. So f prime of x I'm going to think of as 2 times the derivative of just x to the first power. Okay? This is a prime, this is a 1. Okay. Right? So the reason that I'm able to do this is because of that theorem 2.3.4, right? This is because of 2.3.4 that I'm able to say that. And now theorem 2.3.3 tells me that I can use power rule to rewrite this as 2 times, I can bring down the 1 times x to the 1 minus 1 is 0. Well, anything to the 0 power is just 1, right? So x to the 0 is just 1. So this is just 2 times 1 times 1, which is just 2. You don't need to go through all of these steps every single time. I just wanted to show you the justification for why the derivative of this function is 2, but there you go. I guess more generally, it's like if you have f of x equals, it doesn't even matter. Like you could have, square root of 3 times x. And then you could say, what's the derivative? Well, that's just going to be square root of 3. But what if you had something like f of x equals 3x to the 7th, right? The derivative is not just 3 in this case, because now you have to pull down the exponent and then subtract 1 from the exponent. So really we would say f prime of x is 3 times 7x to the 6th. Okay, so that would be 21x to the 6th. Let's do f of x equals 1 over x. Now at first glance you might think, well, what in the world, I mean, that's not a monomial, right? Except that it is. If you rewrite it, right? F of x, 1 over x is just the same thing as x to the negative 1 power, right? And so f prime of x is negative 1 times x to the negative 1 minus 1, which is negative 2. And if you like, you can rewrite that as negative 1 over x squared. Right? So there's f prime of x. So you can see that even with just the 3 rules that we've introduced so far, you get a lot of use out of them. And we're about to give you another rule that'll be pretty nice as well. But let me give you a couple more examples. Let's say that f of x is 5 times the cube root of x. Okay, same deal. You can use power rule on this one. We can say f of x is 5 times x to the 1/3 power, right? Remember, the cube root is the same thing as x to the 1/3. So then f prime of x is going to be 5 times 1/3 x to the 1/3 minus 1. That would be negative 2/3, right? So that's 5/3 times x to the negative 2/3, or if you like, you can call it 5 over 3x to the 2/3 power. That's how I like it. That's how I prefer it. I think it looks better that way. Okay. You could even go one step further and change it back into a radical and call it 5 over 3 times the cube root of x squared, right? If you like. Let me give you one more though. So let's do f of x equals x to the pi. X to the power of pi. Well, same thing, right? We would just say f prime of x is pi times x to the pi minus 1, and that's all there is to it. Okay? So this power rule is really nice. It helps us take derivatives of all kinds of monomials. Okay. So let me give you another rule that also comes in handy. This is called the sum and difference rules. Okay? So what the sum and difference rules tell us is that the derivative, you can distribute the derivative across additions and subtractions. So if you have some function f of x plus g of x, or f of x minus g of x, and you want to take the derivative of it, well, you can just take the derivative of each individual component and then add them up, or subtract them, as the case may be. That's really pretty nice. It's not something to be taken for granted. And I'll tell you right now, it's not true for multiplication and division. Okay? We're not going to talk about those rules right now, but we will soon. But yeah, it's not true for multiplication and division, but it is true for addition and subtraction. Okay? So, and here's the proof that it works. I'm just going to prove the case for addition. Subtraction would go similarly, but if we want to take the derivative of f of x plus g of x, we would do limit as h approaches 0 of f of x plus h plus g of x plus h minus f of x plus g of x all over h. But you can rearrange the terms, right? You can take this negative f of x and put it together with the f of x plus h. You can take this, when you distribute the negative here, you'll have a negative g of x, and you can take that negative g of x and put it together with the g of x plus h. Okay? And then you can split the numerator so that you've got f of x plus h minus f of x over h, and g of x plus h minus g of x over h. Well, this is just the derivative of f, and this is just the derivative of g, right? So you can distribute across addition. You can also distribute across subtraction. Let me give you a few examples of this in action. So find dy dx. Well, that's just another way of saying calculate the derivative, right? But let's find dy dx if y equals 2x to the 6th plus x to the negative 9. Now imagine doing this the long way with the limit definition, right? That would be kind of a pain. But we've got power rule, we've got sum and addition rule, right? We have that constant rule, so this is pretty nice, right? We can say dy dx is going to be 2 times 6x to the 5th plus negative 9 times x to the negative, well, negative 9 minus 1 is negative 10, right? So in other words, that's 12x to the 5th minus 9x to the negative 10. If you want, you could flip it over and stuff. Okay, but that's that one. Let's do y equals square root of x minus 2x divided by square root of x. And you might be thinking, yeah, but those are not that's not a polynomial, right? Like those aren't individual monomials. How do we deal with that? Because I just told you a second ago that you can't distribute the derivative across division. So you can't just take the derivative of the numerator and then take the derivative of the denominator and then put them together. It doesn't quite work that way, as we'll see pretty soon. But what do we do? Well, I can rewrite this as root x over root x minus 2x over root x. Okay? So that's 1 minus This is x to the first divided by x to the 1/2. That's just going to be x to the 1/2, right? 1 minus 1/2 is 1/2. Okay, so that's just the original function. So the derivative, dy dx, is going to be, well, the derivative of a constant is 0. And then this derivative is going to be 2 times 1/2 x to the 1/2 minus 1. That's negative 1/2. So we can clean that up a little bit. Negative 2 times 1/2 is negative 1. This is just negative x to the negative 1/2. Or if you prefer, you can think of it as negative 1 over square root of x. Okay? So there you go. That's that derivative. Okay? One more. Let's say we've got y equals 3x to the 8th minus 2x to the 5th plus 6x plus 1. Okay? Then dy dx is going to be 3 times 8x to the 7th minus 2 times 5x to the 4th plus 6 plus 0. Right? So I'm just taking the derivative of each one of these things individually, and then I can clean it up, right? So I've got 24x to the 7th minus 10x to the 4th plus 6. And that's all there is to it. So it's really pretty nice, I think. Okay, let me give you another example. At what points, if any, does the graph of f of x equals x cubed minus 3x plus 4 have a horizontal tangent line? Okay, well, if the graph has a horizontal tangent line, that means the slope of the tangent line is 0. That means the derivative would be 0. Okay, so let me walk you through that again, right? If it has a horizontal tangent line, that means the slope of the tangent line is 0, because it's horizontal, right? So you have no rise. So it's a 0 rise over a run, so you're going to get 0, right? So if you have a horizontal tangent line, then the slope of the tangent line is 0. Well, the slope of the tangent line is just the same thing as the derivative, right? So in other words, we're looking for where the derivative of the function is equal to 0. So, we want f prime of x to equal 0. Okay? Well, so let's figure out what f prime of x is. It would be 3x squared minus 3 plus 0. So I'm just going to say 3x squared minus 3. And now we want to set that equal to 0 and solve for x. So we would get 3x squared equals 3, x squared equals 1, x equals plus or minus 1. There you go. I suppose, they asked us at what points, and these are just the input values. So if we wanted to come up with the output values, we could plug these back into the original function, right? So we could say, well, f of negative 1 is negative 1 cubed minus 3 times negative 1 plus 4. That's negative 1 plus 3. That's 2. 2 plus 4 is 6. And then f of 1 is 1 cubed minus 3 times 1 plus 4. That's 1 minus 3. It's negative 2. Negative 2 plus 4 is 2. So at what points does it have a horizontal tangent line? It has a horizontal tangent line at the point negative 1, 6 and 1, 2. Okay. Okay, so that's that. um, I want to talk about higher order derivatives. They're not complicated. A higher order derivative is just the derivative of a lower order derivative. So in other words, right, the derivative of f prime is called the second derivative of f, and we denote it by f double prime. Okay, so f double prime of f is just the derivative of f prime. Sorry, f double prime of x is just the derivative of f prime of x. And similarly, f triple prime is just the derivative of f double prime. And f, I don't even know what we would call this, quadruple prime, I guess, but but we put the, when the number is in parentheses, that means take the derivative 4 times, right? So it's just the derivative of f triple prime. And f, the fifth, that's what we would call it. We would call this the fourth derivative. Is just the derivative of the third derivative. And the fifth derivative is just the derivative of the fourth one, and so forth. As always, you know, there are other notations for this, right? We know that y prime could be expressed as dy dx. That could also be expressed as d dx of f of x, right? So then f double prime, the corresponding notations for that would be d squared y over dx squared. Or in other words, it would be d dx of d dx of f of x. That's where you see like the d's get squared there, and then the dx's get squared there. I mean, it's just a notation, right? It's just a notation. But this is another way to say it, d squared over dx squared of f of x. Same thing, well, not same, but similar thing for y triple prime and so forth. Okay, so I just want to give you one example of this. So let's say that f of x is 3x to the fourth minus 2x cubed plus x squared minus 4x plus 2. And let's say that we want to find the fifth derivative, right? So how would we do that? Well, in order to get to the fifth derivative, we have to go through the first 4. Okay, so let's do it. Let's get started. F prime of x is going to be 3 times 4x cubed minus 2 times 3x squared plus 2x minus 4. So in other words, 12x cubed minus 6x squared plus 2x minus 4. Okay, so there's the first derivative. Second derivative. I'm just going to cut to the chase, and I'm not going to write out this middle step. I know that I'm going to be doing 3 times 12, so that's 36 x squared. Here I'm going to have 12x to the first power, and then here I'm going to have 2. Okay, so there's f double prime. F triple prime. 36 times 2, 72. Minus 12, and then that's just 0. F fourth derivative is just going to be 72. So the fifth derivative is just going to be 0. And then every derivative after that is also going to be 0, right? So the sixth derivative is going to be 0, the seventh derivative is going to be 0, and so forth. But there you go. All of that work for an answer of 0. Anyway, so that's that one. And that's all I have to say about that section.